I'm Mohammed Kashkush, and for our senior project, we decided to design and manufacture antibacterial surfaces.
Welcome to LAMP. LAMP stands for Laboratory for Advanced Materials at Pittsburgh, a research group led by Professor Paul Liu in Pitt's IE department that designs and studies advanced materials. Through LAMP, Muhammad and I had the opportunity to manufacture some of these advanced materials at nanomanufacturing and surface characterization facilities located at Pitt and Carnegie Mellon University. Bacteria adhere to surfaces, proliferate, and form biofilms. This contributes to quite a few problems, such as the 8.7% of global hospitalization resulting in healthcare-associated infections. This also leads to biofouling on wet industrial surfaces, which is a major issue for the shipping industry. There is a growing push towards manufacturing these surfaces that could resist these film-forming issues. There are two approaches to antibacterial surfaces: bactericidal and antibiofouling. Bactericidal means to kill the bacteria upon attachment, while antibiofouling repels the bacteria from attachment.
Medical applications for these surfaces include surgical devices, contact lens cases, and touch surfaces such as tables, handles, and even toilets. I collaborated with the Hatful Lab in Pitt's Department of Biological Sciences to grow bacteria and observe what happens when it is exposed to bactericidal surfaces.
Additionally, Dr. Robert Shanks and Nicholas Stella with the Department of Ophthalmology at the UPMC Ear and Eye Center will help designing the antibiofouling approach.
For bactericidal surfaces, I designed and fabricated silver-coated silicon nanocone arrays. I'll take you through the process. To begin, I used nanosphere lithography to manually anneal polystyrene nanospheres onto silicon chips. This creates a close-packed hexagonal monolayer on the surface that serves as a mask and selectively protects silicon from downstream etching processes. Ordered vacancies between the close-packed spheres, however, are exploited in the etching process. So the initial diameter of these refrigerated spheres, which ranges from 500 nanometers to 1.4 microns, also plays a significant role in downstream geometric control of the nanocone arrays. Reactive ion etching, or RIE, is then used to strategically direct oxygen plasma towards the nanospheres, reducing their diameter by 80 nanometers per minute. This planar etching effectively increases the size of the initial vacancies, leaving behind gaps that can later be exploited by high-energy etching methods. ICP-RIE directs high-energy plasma at the samples by flowing sulfur hexafluoride at 33 sccm, octafluorocyclobutane at 82 sccm into an electromagnetic potential formed from a 600-watt coil and 20-watt platen. The ICP-RIE duration governs the pitch of the nanocones, or center-to-center distance between one nanocone and the next, of the array. This process step was conducted at Carnegie Mellon University's NanoFab. After ultrasonication, the net result is an ordered silicon nanocone array. To finalize production, however, we need to add silver. The electron beam evaporator essentially superheats silver in a chamber that cools and allows it to deposit onto the nanocone array. For each prototype, 80 nanometers of silver was deposited. The team and I successfully fabricated 3 bactericidal surface prototypes for comparison. Between prototypes, the varied design parameter was pitch, which were 500, 800, and 1400 nanometers. After allowing Staphylococcus epidermidis to interact with these prototypes at the Hatful Lab, we found that the silver-coated silicon nanocone arrays eliminated all bacteria within 1 hour. So, the bactericidal surfaces that we designed do their jobs effectively, however, all of our prototypes performed equally to one another.
Now let's look at approach B, creating an anti-biofouling surface with reactive ion-etched polypropylene. Polypropylene sheets are hole-punched into circles of equal size, and then washed with a rinse of acetone, methanol, and IPA to remove all organics. Then dried with nitrogen gas. Next, samples are placed in a plasma cleaner inside the lamp to fully clean the surface. This process differs from the RIE by using a diffusion process instead of direct ion etching. Samples are then loaded into the RIE in the clean room, and parameters are set based on the specific recipe desired for the design. Samples are unloaded and tested for characterization or bacterial adhesion. SEM imaging demonstrate the different physical morphology at the micron level that occur to the surface after different RIE treatments. Furthermore, surface adhesion is greatly influenced from the process. RIE treatment can create hydrophilic and hydrophobic surfaces on polypropylene depending on the gas, pressure, power, and duration adjusted. The hydrophilic samples, along with untreated polypropylene, were tested to observe differences in E. coli bacterial adhesion quantities. As you can see, low-power oxygen RIE recipes can reduce E. coli adhesion on polypropylene almost threefold. Here are two fluorescent SEM images of untreated versus treated polypropylene after exposure to E. coli. Lastly, to improve our process, surface chemistry of the surface after treatment were analyzed via XPS. We learned different recipes led to an increase in atomic percentage of various contaminants, particularly fluorine, highlighted in red. By reducing our RIE power to eliminate contaminants while still creating hydrophilic surfaces, we were able to optimize our bio-antifouling process for polypropylene.